the text gives an example of the limit as x goes to 0 of sine x over x by doing a graph of sine x over x and showing that that graph approaches the value 1 as x approaches 0. And they do this by way of showing an example where continuity is important. If the sine x over x function is continuous, and it looks like it ought to be from the graph, then that's a good argument. It's a good intuitive argument, and it's an important argument. There's nothing wrong with that. I'm going to supplement that argument with another idea. If we graph y equals x, we get a graph that comes up through the origin at a 45-degree angle to both axes into the first quadrant. If we graph y equals sine x, we get a graph that parallels this graph for a brief instant and then very slowly moves away. And it's important to understand that as x approaches 0, okay, x gets smaller and smaller, the sine of x gets closer and closer to the value of x. For example, if x is 1/10 here, then y is going to be 1/10 on the y equals x graph, obviously. And the sine of x is going to be very close, just a little bit less than 1/10. You should check that out on your calculator. Put in 1/10. Make sure you're in radian mode. Never do calculus when you're not in radian mode. Forget about degrees when you do calculus. And you will find that the sine of x is just a tad bit less than 0.1, 0.0999 something. Very close to 0.1. So that, again, from that experience we can see, and from the picture in the graph, we can see why sine x over x ought to be 1. We're dividing the height of the blue graph by the height of the green graph, and the heights merge. They become the same. So we're dividing a number by itself as we approach 0.